The size, however, should be larger enough to fill the molten metal in the mold cavity without any lapse, seams, or misruns. If a single sprue is not adequate to fill a large casting in a required time, two or even more sprues may be employed. 2. As the metal leaves the pouring basin and falls through the sprue, it is under constant gravitational acceleration. The further the metal drops in the sprue, the greater it is accelerated, and so the velocity of the metal near the bottom of the sprue is considerably greater than the velocity of the metal at the top of the sprue. Volume flow rate, however, must be the same at all points in the sprue, and so the steam contracts at its force. This contraction creates a partial vacuum between the sprue walls and the metal steam. The air is aspirated into the metal. So this the sprue, after the pouring base, the sprue is just a gate, a means of transport for the metal, for the molten metal. So it, as the metal touches the basin, pouring basin, it goes through the sprue. The sprue is just a mold wall, like it goes vertically into the gate. So it's just like a means from the pouring basin to the gate. So that's the sprue. It's just an internal structure. So you see the picture above, you see the straight sprue corners, you see the tapered sprue rounded corners, and plus whirl and pouring basin, you know. So we have severe aspiration and negligible aspiration. So all these are about the sprue walls and how it is being used. So if however a sprue is employed whose walls are not parallel but are tapered, the metal can lie firmly against the sprue walls. As it travels downwards, the air aspiration can be eliminated. Simple calculation gives a close approximation to the amount of taper necessary. The application equation is A1 under 2. You can see the formula there. So we are A1, the area of sprue entrance, A2, the area of sprue base, Z1, depth of metal in pouring basin, Z2, distance from metal level in pouring basin to base of sprue. That's the formula. So you have to consider this in constructing your taper in the sprue. Number 3, a further refinement of sprue design, which significantly reduce turbulence in the sprue and substantially increase flow velocity with a given size sprue, is to reduce the sprue entrance in the design you are seeing above. They say it has been shown that where the sprue entrance is sharp cornered, contraction effect can diminish flow to 70% of that theoretically position. As possible as formed an air pocket with resultant air entertainment, reducing can increase.